ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you for tuning in. What we're going to do today is we're going to take a look at solubility equilibrium. And so a lot of you, right off the bat, when you look at this title, you're going, wait a minute, Mr. Doolin, equilibrium and solubility? Something's either soluble or it is insoluble. And that's what we really think of when we refer back to our pre-AP roots, is we learn that something's either insoluble or something is soluble. Well, that's technically not the complete story, all right? And so to define these two terms, we would say something is soluble if greater than 3 grams of a substance will dissolve in 100 milliliters of water, all right? And something is insoluble if less than 3 grams will dissolve in 100 milliliters of water. And so if we're looking at solubility and we understand we're going from dissolving some solid, so I guess give a general reaction. If I'm going I guess I do AB to solid, doing A plus B minus, that if something that's greater than 3 grams, right, I'm going to say my KSP for this particular situation is greater than 1, which means my products are favored, and I don't have very many of the reactants or the solid left by the time this thing dissolves. And so we say we get full dissolution or dissociation of this ionic compound. All right? But insoluble, it means that less than 3 grams, so generally my KSP value on this is less than 1, which means reactants are favored in this particular case, and I don't get very many ions produced. So this is really where we are going to pin our focus for this particular part of the unit, is that we're going to be concerned with, like that plastic water bottle that you're drinking out of. Does the plastic actually dissolve in the water? Well, most people would say, well, heck no, Mr. Dillon, it doesn't dissolve in the water. It's insoluble. Well, technically that's not the whole story, right? It just means that less than 3 grams per 100 milliliters of water will dissolve. Right? So some of that bottle actually does dissolve in the water, and that's what we're going to be taking a look at today, is how do we calculate that amount that will actually dissolve in the water. Now, there's some vocabulary that we are definitely going to have to get out of the way. The first is what KSP is. KSP is called the solubility product. And what it does, and it's really just for ionic compounds, it's that equilibrium value. It's what we're talking about up here. Normally, if you're given a KSP value, it's going to be very, very, very small, all right? On the orders of e to the negative 5, e to the negative 10, e to the negative 18th, something that's very, very small. The next term that I need you to be completely familiar with is called molar solubility. And what molar solubility is it's moles per liters, i.e. molarity, right? So moles per liters of substance that will dissolve. Now, when we're thinking about equilibrium, you know the quack table, so this value is actually equal to your X value in the change row of your QCK table. All right? And it's very important that you understand the distinction here, that it's equal to X, not 2X, not 3X, but just X, right? It's equal to the X value from your QCK table. The next one that also, it gets kind of tricky here, is called solubility. And what solubility is, it's grams per liters, right? Not moles per liters anymore, but grams per liters of your substance that is dissolved. And most of the time, if we're being asked for solubility, we have to convert that from molar solubility into solubility, because remember, if I'm using a QCK table, I can use molarities or I can use pressure values inside of that table. I'm not using anything else, okay? All right, so 3 very important words here, right, to keep straight as we move through this. Okay, so one of the first examples we're going to look at is the dissolution of silver chloride. Now, silver chloride dissociates into Ag plus and Cl minus. Notice here it's got a 1-to-1 ratio of the ions. The KSP value for this sucker is equal to 1.6 E negative 10. So notice it's not very soluble. I would say that I would describe this as reactants are favored, so I'm not going to get very many of these ions in solution. Well, go ahead and write our KSP equilibrium expression. You'll notice it's just Ag plus times Cl minus. Now, I don't have any of the solid, involved in these KSP values or these KSP expressions. And please understand that, because remember, part of writing the equilibrium expressions is we leave out solids and liquids. We leave out those pure substances. Okay? So now let's set up a QCK table, and let's just say I'm going to drop some silver chloride into water, and I want to know what's the concentration of these particular ions after equilibrium is reached. So I'm just going to scratch through that part because I have a pure substance. I'm not going to let it confuse me in my QCK table, right? And so we're going to assume that I drop it into water. My change values are going to be X and X, right? And so if I were to set this up, I'm going to have KSP equal to X squared, right? Well, remember, X, this value of X is actually my molar solubility. So a lot of the times you'll be asked, what's the molar solubility of this particular substance when equilibrium is reached? And so what they're telling us is we need to use our QCK table to actually solve for that X value. And so all I would do is set this equal to 1.6 E negative 10, solve for X, and in this particular case, X is equal to 1.26 E negative 5, and that would be moles per liter. Or you could put molarity there, all right? And so not anything crazy. It's still just equilibrium and QCK tables, but what we have to do is we have to apply new terminology into this situation to talk about solubilities as well. And so here we go. If we've got K values, you know we're going to have Q values. So what do our Q values mean in this particular case? Well, if Q is less than K, remember, if I'm thinking about this products over reactants ratio, what I'm telling you is that I've got too many products and too many reactants and not enough products. So my reaction will go in the forward direction, right? It will head towards products. It will produce more products. So more silver chloride will dissolve. And what we do when we were talking about solutions, we would say this is termed an unsaturated solution. All right. Now, the other is Q equals K, right? That means I am at equilibrium. And when I'm at equilibrium, no more will dissolve, right? Because I've got things going forward and backwards there. And so this is termed a saturated solution. And then the last one, when Q is greater than K, that means I have too many products, not enough reactants. And so what I'm saying is that my reverse reaction is actually favored. I'm going to precipitate silver chloride out of this solution because I'm heading in the reverse direction, and that occurs when we have a super saturated solution. And so they embed this vocabulary into a lot of questions, ladies and gentlemen, to where they're just going to say, hey, I've got a saturated solution. Well, what they're telling you is that you're at equilibrium. Or they say, hey, I've got an unsaturated solution, and what they're telling you is that I'm below my K value, and my forward reaction is actually favored there, right? Is actually going to head in the forward direction, and so I can dissolve more substance. And then the opposite's true for supersaturated. I would actually get precipitation out of there. Okay, so I want to look at one more example here. And so this is lead 2 fluoride. So it's going to go to Pb2 plus 2F minus. And again, my KSP value here is equal to 4.1 E negative 8. So the expression is equal to the concentration of Pb2 plus, and it's very important when you're writing these KSP expressions, ladies and gentlemen, do not leave out the charges. Do not leave out the charges, all right? Because remember, there's a difference between Pb2 plus and Pb. One's solid lead and one's aqueous lead. So set up the QCK table here. And again, just cross out the PbF2, and then I've got 0, 0, X, 2X, X, and 2X. So this is why I'm doing this example, is I wanted you to see the 2X here, because if you actually solve for the solubility, if you're asked to solve for molar solubility, and you calculate it as 2X, then you're actually off. Because remember, molar solubility is equal to that X value. And so again, another important ratio that we run into a lot here is this actually equals 4X cubed. And so that's something I need you, if you don't see why it equals 4X cubed, then I need you to understand and actually figure that out, right? X and then 2X, the 2 gets squared, multiply together, and then I'm in 2X cubed. So my X value, my molar solubility of lead 2 fluoride, for this particular case, actually be 2.17 E negative 3, and that's moles per liters. And I'm not going to convert to solubility. And so all I would do to convert to solubility is it's just a dimensional analysis, a little stoic problem where I would convert moles to grams here. All right? Okay. So moving on, ladies and gentlemen, and those are two very important examples, and we need to understand my KSP values here will be x squared, 4x cubed. I think the other ratios are 27x to the 4th and 108x to the 5th. And those are just your four most common situations, and I'll show you at the end of the lecture how we reach all of those. All right? But it's very important, and you could probably start to realize that my KSP value does give me some hint as to what the solubility of substances is. So the question becomes, if I'm trying to compare two different substances in terms of molar solubility, can I use this KSP value to make a quick prediction about what molar solubility would be for the particular substances? And the answer is kind of, right? As long as your ratios are the same, like your silver chloride here was a 1-to-1 ratio, if I'm comparing silver chloride to another 1-to-1 ratio of dissociation molecule, then yes, I can make a direct comparison of KSP values. And I'm going to be pretty much ballpark, and my prediction will be correct 99% of the time. But if I'm looking at like lead-2 fluoride versus silver chloride, right? One of them has a 1-to-1 ratio, the other one has a 1-to-2 ratio. I can't actually use KSP reliably to make that prediction, all right? And so we have to be careful when we're looking at our ratios and we're trying to use this KSP value to predict molar solubility, right? We have to actually, if I have different ratios, I'm just going to go ahead and solve out for that X value, and then I can directly compare the X values. And so the X for the silver chloride, and this is AgCl here, I don't want to confuse anybody, that was, what was that? That was 1.26 E negative 5 moles per liter. And so if I'm looking and comparing these two, I would say which one is more soluble, which one's less soluble. Well, in this particular case, lead-2 fluoride is actually a more soluble substance than silver chloride because my molar solubility, I'm going to get more moles per liter actually dissociated and dissolved into that solution than I would for silver chloride, right? And so we have to make sure, we have to be careful that we're checking those ratios before we try to make direct comparisons of those KSP values, okay? Okay, so now what I'm going to do is I'm going to go ahead and I'm going to put down common KSP ratios, and I'm going to pause this video, and I'm going to write down all the different scenarios, or the four most common that we will run into, and show you the ratios and show you what KSP equals to. And this is an attempt to save you some time, because if you just check the subscripts on these suckers and actually find these ratios, then you don't have to spend time setting up the quack table a lot of the times, all right? Okay, so my first example here would be AB going to A plus and B minus. We saw earlier this is a 1-to-1 ratio, right? And we understand that KSP is equal to X squared. Okay, my next situation, if this is number 2, I've now got a 1-to-2 ratio or a 2-to-1 ratio. It doesn't really matter. But my KSP value in this particular case is always going to end up equaling 4x cubed. So whenever I've got subscripts and my ions here, my cation and anion, have a 1-to-2 ratio or a 2-to-1 ratio, KSP is actually going to equal to 4x cubed. And that's 100% of the time, ladies and gentlemen. My third one is when I have a 3-to-1 ratio. I'm not going to write the bottom dissociation reaction. You probably should, just to get some practice here. So this is a 1-to-3 ratio, right? And in this particular case, and this might be something that you want to work out, but I'm just going to tell you what it is. This is actually equal to 27x to the 4th. And so if you set up the KSP equation, the equilibrium expression, right, and actually substitute in your quack table values, those change x values, then you'll end up with 27x to the 4th. And if you don't see it in your head, I strongly encourage you that you take a second and you actually solve that out to show and prove to yourself that that's equal to 27x to the 4th all day long. Okay, and then my last example, I'm looking where I've got a 2-to-3 ratio, right, and my KSP value in this is equal to 108x to the 5th. And again, that's all day long. I encourage you to write that second dissociation reaction. I encourage you to set up the quack table to actually show yourself and prove to yourself that this is going to equal out to 108x to the 5th, all right? Okay, ladies and gentlemen, so that wraps it up. There was a lot here. There's a lot of vocabulary in this, just nuances of how you're supposed to use vocabulary. So I hope you paid particular attention and got all those extra things that I said out loud and didn't necessarily write down involved and included into your notes here. If you have any questions, I hope you got them written down. I'll see you in tutorials for those, and then otherwise I will see you in class.